itself. So for the general case, we have E is, any ellipsoid, and A is any vector. Again, what is A? Our algorithm checks whether C is in a polytope. If not, we return A as the normal of the violated inequality. And so we can find an invertible affine transformation that maps, I'll call this T, that maps T of E is equal to F, in other words, E of identity around 0, and maps A to that same vector that we used before. And you can check that that multiplication or that mapping by T commutes with the ellipsoid update rule. So now the key is that for any two ellipsoids, so for any ellipsoids, E1 and E2, obviously in the same space, and any invertible affine transformation, the volume of T of E1 divided by the volume of T of E2 is exactly equal to the volume of E1 divided by the volume of E2. So multiplying by an invertible transformation does not preserve volume, but it does preserve ratios of volumes. And therefore, the special case that we did on the previous slide is essentially the general case, because we can reduce anything to that special case by this invertible transformation T. So in other words, we are back to the special case. And that is essentially, with some details omitted, but essentially the core of the idea of this volume reduction. These are useful facts to know about ellipsoids and just general geometry in n dimensions. So where are we so far? We know, first of all, how to compute the Loevner-John ellipsoid of half of an ellipsoid. And we also know that this Loevner-John ellipsoid procedure is going to shrink the volume by a constant factor, a factor that depends on dimension, but not where we are on the iteration at every single time. So far so good. So we know how to run the simplex algorithm, and we know that eventually the algorithm is going to either have a point in P or have an ellipsoid of very, very, very small volume. So we have a few details that we still need to work out, and in particular, we need to know where to start, how big to start our ellipsoid, and we need to make sure that this starting ellipsoid isn't going to have to be astronomical with respect to the encoding length of our polytope. And then we also need to know when can we stop. So our assumption here is that we are given a polytope that is either empty or contains minimum volume. But in fact, we don't have to assume this. We have the following two results. So the first lemma gives us an outer bound on our polytope. So it guarantees that our polytope is circumscribed. If P is equal to, so I'm bringing now, again, comment on notation. This is now an A that has nothing to do with the A that's defining my ellipsoid. It's just an A that's defining the polytope. This is contained in the unit ball of radius around 0 of radius r, where r is equal to square root of the dimension n times 2 to the, now this notation means the description length, the number of bits needed to describe the matrix A and the vector B that are defining the polytope, minus n squared. Okay, so AB, this is notation. It's not some kind of dot product or something like that. It's the encoding length of A and B. So perhaps at this point you're somewhat unhappy because I promised you that we motivated this problem by saying that all we have is this oracle that either guarantees that you're feasible or it provides you a violating hyperplane, so that makes an inequality that's violated. Whereas now we're seeing that our initial ellipsoid, and therefore the number of steps, is actually going to have to depend in an exponential way on the description length of my polytope. So you're correct in being concerned about that. Well, we're gonna revisit that in a minute. But at least let's keep to the internal consistency of the ellipsoid algorithm. This is saying that if you have a polytope that's defined by rational coefficients, then without knowing anything else, without doing any computation, you know that it cannot be too big. And note that we've assumed that it's bounded. Again, these are things that we can remove. If P happens to be full dimensional, and therefore not empty, then we also have a lower bound on the volume of P, where the lower bound also comes from the description length of the vector A, of the matrix A. So its volume is at least some number, 2 to the minus n plus 1 times the description complexity of A plus n cubed. And so this is telling us that you have a polytope, there's an efficient description length for A and B, or what we care about is what that is, and these two lemmas, which we're not going to go into their details, promise us that we can initialize the ellipsoid algorithm, namely you initialize it with the unit ball of radius r, centered at the origin, and then you proceed from there. And moreover, we also know when to stop, because when eventually our ellipsoid EK, after k iterations, if that has volume that's less than this lower bound, then we know that we can stop our algorithm, and our polytope P is empty. So let's just put this all together. So basically, we initialize with E0, which is an ellipsoid defined by A0 and C0, where A0 is, again, going to be r squared times the identity, where r is as given in the previous slide. So r is equal to square root of n times 2 to the a b minus n squared, and C0 is just the origin. And then on iteration k, ek is just going to be e of ak ck. If the center is in P, then we stop. Otherwise, we know that there exists some vector a hat that cuts my ellipsoid, such that a hat times transpose x is less than a hat transpose that center, which was not in P, for any x in P. This is what we are given. And then we use this a hat to define the new center and the new positive definite matrix as the explicit formulas define. And once we get up to k, if we haven't stopped, if k is equal to some number, which is just a calculation here based on our bound on how much the volume shrinks, 2n times 2n plus 1 times the description length of A plus n times the description length of B minus n cubed, we stop and we return that P is empty. So this is the summary of the ellipsoid algorithm. Okay, so now let's look at this and think about what do we still need in order to be able to use it for our motivating problem, which was this R arborescence problem. Is it really fair statement that if our polytope is not explicitly given by A and B, but rather just given by this by a separation oracle, in other words, something that where you feed it CK, let's look at the definition of the algorithm. What do we really need here? Do we ever really need the set A? I'm sorry, the matrix A and B that defines the polytope. Do we ever use it? And we don't actually ever need it explicitly, except for in this step, we need to be able to tell feasibility. So we need to be able to determine that. And we also need to be able to produce a violated inequality that cuts my ellipsoid in half. And recall from the lecture on the R arborescence problem that by using Ford-Fulkerson and solving a max flow or several max flow problems, we were able to do exactly what is required for this step of the algorithm. So what's left for us to assert that that's enough? Well, what's left is what this number n is here. So you see that this number n is and also what R is. So we need a bound on the description length of A and B, not for any purpose in terms of running the algorithm, except for knowing how to start and knowing how to stop. And so let me just summarize this, and that is basically the algorithm only needs the description length of A and B to initialize, because we initialize at E0, which is E R squared I 0, and to know when we can stop and declare that P is empty. So in particular, if somehow you had side information or you had additional information that told you that here's a polytope, I refuse to give you an explicit description of the polytope except through this oracle. Again, think of the arborescence problem. We would never write down A and B. There are exponentially many constraints. But we have an oracle which can efficiently either certify that a candidate point is feasible, or it can find a violated inequality. So imagine that we have that. That's our separation. That's what's called the separation oracle, and we'll be defining this more precisely in future lectures. So if we have that, and we have side information that tells us that our polytope is contained in a particular set of radius capital R, and is contained in a sphere of radius capital R, and perhaps contains a small ball of radius little r, and hence that would give us a lower bound on the volume, that would actually be all that we need. In that case, our algorithm could start based on that side information and could terminate based on that side information. So the upshot here of what I'm saying is that our algorithm only needs some knowledge of R, and, which is basically a circumscribing radius, and let me just call it little r, which is a ball, some ball that's contained in our set, in our polytope P. And otherwise, there is nothing here that forbids us from having exponentially many inequalities defining our polytope, as long as we have an efficient way to search through them and check that they're all satisfied or find the violated one. And this is exactly how we're going to use it. Now, just a historical note on the ellipsoid algorithm, it was already a breakthrough the way that I presented it, where we are basing the radius, capital R, and this lower bound on volume on the description length. Already this was a breakthrough, but it is, and it's applicable to any explicitly specified linear optimization problem with rational coefficients. Full stop. It's already a very powerful statement, and really represented an algorithmic and mathematical breakthrough. Beyond that, we can now use it for combinatorial problems that are specified through this separation oracle. And this is what we're going to be moving into next. I want to make some final comments, which is that the method we presented is called, for I think natural reasons, the central cut ellipsoid. Natural name because at every step we're cutting the ellipsoid in half. But there are other cutting methods that define the ellipsoid whose proof proceeds in a very similar scheme. So there are other related approaches, which we're not going to talk about right now, but you can read about shallow cuts or deep cuts, and potentially other variants. We're going to stop this lecture here, and in the next lecture, we're going to make more explicit the connection between the ellipsoid algorithm and optimization.